Uh, Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker. Our speaker is Bogdan Raonic, and who's currently a PhD student at ETH Zurich. He completed his bachelor degree in physics and mathematics in École Polytechnique in Paris, followed by a master's in applied mathematics at ETH. His research lies in the intersection of deep learning and scientific computing with a focus on physics-based machine learning and neural operators for solving partial differential equations. He's currently also interested in foundation models for physical systems and the use of generative AI in turbulence modeling. Raonic, thank you so much for your time today. We're all excited for your talk, and with this short introduction, you can begin.
Thank you for inviting me. Let me see what time it is. Okay. Thank you for inviting me. So as you said, my name is Bogdan. I'm a third year PhD student at ETH, and my research, I'm associated also with math department at ETH and also with ETH AI Center. And uh, today's talk will be about operator learning for PDEs. I will explain every word very soon in my slides, but yeah, we can start. So 1 second. Okay. So I first wanted to show my group and collaborators. Many of them are now professors at different universities, so they left Zurich. My advisor is Professor Siddhartha Mishra, and the others here on the slide are my collaborators and friends who wrote papers with me. So today I'll firstly speak about numerical methods and why we need deep learning and why this new paradigm or relatively new paradigm of deep learning in scientific computing was why it appeared in our research and why it is important for us. Then I'll speak about neural operators and convolutional neural operator that we developed in my lab. Then I'll move to Poseidon, which is a foundation model for PDEs, the first version that we developed last year. And then finally, if I have time, I'll speak about generative AI for turbulence modeling. And all, actually, we are in my lab very interested in turbulence and in fluid dynamics. So that's why we started that project. We'll see if we have time to talk about it. So, as many of you know, partial differential equations are all around us. So we can describe fluid motion, we can describe tsunamis. I usually don't put this tsunami slide because it's mostly fluids on this slide. But we can also describe different materials, also weather forecast, which is described with fluid-like equations and many other things, also chemical reactions, etc., etc. So the world is, or the nature is described or modeled by these partial differential equations. And when we talk about solving PDEs, what it means by solving is approximating or solving for this solution operator of PDEs. And in what how can a solution operator be described is imagine you have a weather today, and a solution operator could be to describe or to find out what is the weather tomorrow or in 1 year or in 10 years, depending on the time horizon. But the solution operator itself takes as an input some input, let's say weather, and some boundary conditions, other forcing terms, and it provides the approximation, or it provides a solution or the weather at the time t in the fixed time t in the future. So that's like a fixed in time solution operator, and we'll mostly work in this presentation with those solution operators and the ways to approximate them. So let's go back and see how in the past centuries those solution operators were approximated. So we usually use numerical methods to approximate them, and there are different kinds of numerical methods, such as finite difference, finite element, finite volume, and as many of you know, there are a lot of researchers working on these numerical methods. However, they're for most industrial-based problems and big problems that we want to solve in science, they're very expensive, especially for example, for instance, for uncertainty quantification, for inverse design. We have to run them many times, and since they're data agnostic, so they're unable to learn from available data sets, we have to run them many times. Um, Also, we need to know exact physics of the problem in order to integrate them, which means that for weather forecast, for instance, or some different real problems in nature where we don't know the exact physics, we have to model first the nature itself with some realistic or unrealistic models, and then to integrate the physics using the numerical methods. And they also approximate the solution on a mesh or a grid. So in problems, for instance, the turbulence in fluids, we can't resolve all the scales in the problem, which is problematic because we sometimes really want these detailed or these small scale features to appear in our approximations. So we have to increase the mesh size, to decrease the mesh size, and then the numerical methods become even more expensive. And also they usually require PhD level experts for running them, meaning that for very difficult problems, we really need to pay someone to write the code and to run these methods. So now let's go to deep learning. So let's say that we have some available data sets. Either we collected the data using the measurements, or we generated them using the numerical methods, and we want to solve a solution operator given this data set. This can be useful, for example, for many query problems. Imagine that you have just a small available data set, and then given this small data set, you want to do uncertainty quantification, but you don't know, you can't do it accurately with small amount of data, so you need to find or approximate the solution operator using a surrogate model, and that's where the deep learning pops up, and especially neural operators. So what those models are, they are purely data driven. In this case, purely data driven models, and they solve the equation for a family, or approximate the solution of the operator for a family of PDEs with a single set of parameters. And they're possibly slow to train, but much faster to evaluate compared to conventional numerical methods. And what now I go to the theory of neural operators, and what we actually want to do is to approximate operators, which means mappings between function spaces. And as we know, functions themselves are continuous. So we first have to figure out the way to approximate the mappings given the data, which is discrete always on the computers. And then we need to understand how these discretizations impact our approximations of the operators. So the neural operators are the approximations of the solution operators that are so-called mesh independent, meaning that we are able to use different meshes or different discrete representations of our functions as inputs, and we still get reasonable outputs or accurate enough outputs. So let's say that we start with the input vorticity, which is a function. We use some discrete representation of this vorticity obtained by some numerical methods. And then we approximate, using the neural operator, we approximate this function on a grid level, so at the discrete level. And then finally, we use some smart kind of interpolation that brings us back to the function space. And this is exactly what I was speaking about. On this slide, we see that at least the theory that we developed in my group, which is called or the models that we developed, they are called representation equivalent neural operators. In these representation equivalent neural operators, we have equivalence, as the name says, equivalence between the continuous spaces or the function spaces and the discrete function spaces. And we want our model to be able to go back and forth. So we want to train the model at a discrete level and then be able to represent it at the continuous level as well. Also, if we change the discrete representation of our model, so if we change the basis of the discrete space, we still want to be able to go back to the continuous space. So the goal itself is to design our model in such a way that learning at the discrete level, so at the discrete level we have the data, which we again obtain either by measuring in the nature or using some surrogates or numerical methods. So we want to design our model in such a way that learning at the discrete level is equivalent to learning at the continuous level. Now, next thing that I want to speak about is how we came up, why do we use convolutions? I said that we're going to speak about convolutional neural operators. So in this area, the convolutional neural networks were abandoned because of their finite dimensional nature. So they're really scale dependent. And since they used to be efficient in small scale research in many image processing problems, um, we wanted to figure out a way to basically change the way we observe the CNNs and make them be neural operators. Um, Also, the CNN have this aliasing phenomenon, and all the models that we have in this area. And let's sorry, there is some issue with my slides. So let's explain what this aliasing phenomenon is actually and why we need to change all the operations that appear also in the existing neural operators in order to have really continuous discrete equivalence, the property that we spoke about in previous slides. So imagine we have a signal. At the bottom, it's the signal in the physical space. At the top, it's a signal in the frequency domain. And imagine we apply activation function. So let's say value or swish or any your favorite activation function. And since the data itself is represented with the discrete level, according to Nyquist-Shannon sampling theory, there is a maximal frequency that we can represent with that sampling, with the sampling rate of the data. And when we apply activation function on top of this signal, since the activation function has an infinite frequency, so the frequency domain of the activation function is usually unbounded, we get some very high frequencies, higher than the maximum possible frequency at the continuous level. And so since the data itself is still at the discrete level, what happens is the aliasing phenomenon. And in the aliasing phenomenon, the high frequency data that cannot be represented with the sampling rate of the signal. So this high frequency content gets mixed up with the low frequency content, and we get the aliasing error. So the continuous signal and the discrete signal are not equivalent anymore, and we lose this continuous discrete equivalence. So what we need to do is to modify all the operations that we use in order to account for the fact that we deal with function spaces at the discrete level and not just some Euclidean-like spaces. So we developed this convolutional neural operator, which is a UNet-like architecture. It's simply the architecture itself is a UNet, but all the operations, so the upsampling, downsampling, the residual blocks, the activation layer are modified, as I said, in order for our model to be representation equivalent neural operator. So the UNet is just a multi-scale convolutional neural net, where in the beginning we have all the frequencies present, and as we downsample our signal, we basically change the maximal frequency that we can represent, and we get coarser and coarser grid. And then so that's the encoder part, and then in the decoder we basically reconstruct the signal, and using this model we basically approximate the solution operator of a given PD. So the question is, how are all the operations fixed? So we said that CNNs have this scale-dependent nature. So we first changed the convolution by transferring all the inputs and outputs to the fixed computational grid using the sinc interpolation filter. So we either upsample or downsample our signal. Up and down sampling is done using, as I said, the sinc interpolation filter, which is essentially cutting out the high frequencies or adding empty space in the frequency domain depending on the desired resolution. And the activation function is completely changed, and we transform it in 3 steps. So as I said, the activation function causes this aliasing phenomenon that we want to avoid. And how the activation function is done in our paper is in 3 steps, as I said. So first, we upsample the signal before applying the activation function, and we add artificial empty space in the frequency domain for the new frequencies to get introduced. Then, when the activation function is applied, those new frequencies get introduced, the higher frequencies, and since we cannot represent it with the original sampling rate, we simply cut them from the signal, and that's done by downsampling the signal with the sinc interpolation filter. And this is how the CNO is developed. So basically, this is the architecture, and all the operations are modified. And then we tested out CNO on many different PDEs. One of them is this thin shear layer experiment, where in the input we have a fluid moving to the right. So this is on a torus with the periodic boundary conditions. Fluid moves to the right in the middle, and towards the top and the bottom, the fluid moves to the left, and there is a gradient of the velocity field, obviously, which flips the direction of the motion. Then we evolve this input with the Navier-Stokes equations and get the output at a fixed time. And the solution operator is to go from this input to the output. One of the samples is given here. And then we see that the CNO was performing the best among all the baselines. Also, we had this Poisson equation example, and I wanted to explain this slide in detail, so what it means. And in this example, the really aliasing phenomenon hit other models. So imagine this is, I haven't shown for some reason what the exact experiment is. I apologize, but this is the ground truth spectrum. To the left is the ground truth spectrum of the average ground truth spectrum of the outputs that we want to approximate. And then I showed the approximated spectra obtained using different CNO and the 2 other best performing baselines. And we see that the CNO almost perfectly approximates the ground truth spectrum, while the FNO and UNet have these high frequencies present in the spectra, which is due to, we believe, due to this aliasing effect. And so the high frequencies get introduced and by the activation function, so that the FNO and UNet were not able to approximate the ground truth spectrum very well. Also, we tested out the CNO at different resolutions. We said that for null operators, this around the training resolution, it's very important that the model generalizes well. I don't say that it should generalize across all the resolutions. So in the turbulent flows, you cannot discover new physics with these models, but it's important that you can generalize around the training resolution. And we see that the UNet cannot really, due to scale-dependent nature, cannot really generalize across different resolutions, while the CNO and the FNO model, which is one of the most famous, I forgot to say that, one of the most famous, if not the most famous neural operator, they can generalize different resolutions. And CNO, at least in this experiment, was very flat. FNO was also performing very well in this experiment. And then this table shows all the different PDEs that we tested out, and CNO was performed very, very well in all the cases. So now I'll move on to, I took too much time explaining FNO, CNO, sorry, but I think I have time at least to explain Poseidon. So what Poseidon, let's first speak about neural operators in general and why we need these foundation models that are famous nowadays. So as we increase the number of training samples, so imagine that you start with 10 samples, you can only generate, let's say, 10 samples, and you get some error. And imagine that tomorrow you can generate uh, twice as many samples, and you get some other error, and you keep on, and you get this curve, which represents the testing error of your different models that you train versus the number of training samples. And it appears that for all the deep learning models, this testing error scales as a power law with the number of training samples. However, this alpha for all the existing models so far is usually very small. So for difficult experiments, you need a lot of samples in order to get accurate results. We'll come back to this. So actually, we are not going to come back. So I'm going to continue speaking on this topic now. So could foundation models help in this, well, increasing this alpha, or at least uh, pushing down this curve so that with small number of samples we get low errors? So the idea is the following. Imagine we have a lot of fluid, like in our case, fluid-like data, but imagine we have some sort of data and of PDE-like data. We pre-train a transformer model. Why transformer model is because transformers in the LLMs and happen to scale very fast or much faster than the other models. And we also observe that in PDE settings. So imagine we pre-train a transformer model on the available data sets, and then that's step one. And then in step two, we adapt or fine-tune that pre-trained model on task-specific data. And we hope that the learned effective representation that we obtain by pre-training the model on large amount of data is enough to reduce the number of training samples needed to achieve some low error. And we hope that this can provide this two-steps training can provide good generalization to unseen and unrelated PDs via fine-tuning, of course. So let's see how we can use all the available data sets. So what is our goal here? I spoke before about fixed in time solution operators, meaning that given weather today, I fix the time tomorrow and I only approximate this mapping. But all the time-dependent PDs are much different. So we have the whole trajectories. We have so much data in this one trajectory or one solution. And what should be our task? So we believe that our task should be that given the initial datum, so given the weather today, our models need to be able to predict the weather at any given time in the future. So in 1 day, in 2 days, in 3 days, of course, the error itself will grow in time, but we at least want to be able to have some approximation of this solution operator in time. So again, we define our task, PDE task, at least for time-dependent problems, as given the initial datum, so the velocity, the initial conditions, boundary conditions, all the other forcing terms, and all the other parameters. deduce the solution of the PDE in time, but continuously in time. And for that, we have available trajectories, discrete trajectories that we either obtain by measuring in time or generating the trajectories using numerical methods. And this example here is just the seismic wave equation. It's one of the equations we tested out in the Poseidon paper. So what is Poseidon? As I said, the task-specific operator learning that CNO that I explained in the CNO part of the presentation is given the data set, train a model on that data set, test it out on testing data and see how it generalizes. In the Poseidon sense, Poseidon settings or the foundation model settings, we pre-train a transformer and then we fine-tune it on different downstream tasks. And we hope that this this method will make our model generalize better to different tasks. So what is Poseidon? It's a multi-scale time-dependent transformer. So it has this UNet-like architecture, but we don't use convolutions. Instead of convolutions, we use attention and transformers. The Poseidon is pre-trained on a diverse large-scale data set, or large-scale in the PDE settings, and this data set consists of 5 million input-output visual tokens. And it seems that Poseidon has exceptional performance across many PDEs. So we tested it out and we compared the performance of Poseidon to already to existing foundation models for PDEs at that point. Also, we pre-trained the CNO as a foundation model, which is a convolution-based foundation model, and we also compared it to models trained from scratch, so in task-specific settings. And it appears that Poseidon beats all the baselines by a margin in almost every case. And I'll show later or I haven't included the table. You can see it in the paper, but it really has an exceptional performance. The Poseidon, I forgot to say, is pre-trained on fluid-like data, so only Euler equations and Navier-Stokes equations, while we tested it out on different PDEs such as wave equation, Helmholtz equation, also fluid equations, um, Allen-Kahn equation, Poisson equation, which is time independent, and it seems that this is a way to go. So as I said, it generalizes to new and unseen physics. For instance, those three equations that I mentioned. And also, very importantly, it scales effectively with model and data size for both pre-training and downstream tasks, which means that as we increase the model size, we get better performance. As we increase the data size, the pre-training data size, we get better performance. And also at the downstream level. So imagine we have these downstream tasks. So here we just put a few plots of um, model trained from scratch. So in this task-specific settings, we compare these models to the Poseidon performance. So the task-specific is the orange line, the blue line is the Poseidon performance, and you see that in all these, so the Navier-Stokes, compressible Euler, wave equation, Poisson equation, we have much better scaling and much better performance. Note that there is a log scale y-axis has log scale, so we are better than the models trained from scratch by a huge margin. And this is, do I still have time?
Yes. This you can take as long as much as you want.
Oh, okay,
I
sorry. Then I'll
yeah
speak about generative AI and why it is important, at least
yeah.
in
Please
operating.
take
Sure,
please take your time.
perfect. So up to now, we spoke about very well-defined mappings. So, for instance, Navier-Stokes equations with relatively low Reynolds number, where the turbulence didn't appear or haven't appeared yet. Um, we talked about maps that are difficult to approximate, but they are still defined in a very, very precise mathematical way. And now let's try to think about approximating chaotic mappings or the mappings, Lipschitz constant mappings that have very high Lipschitz constant. What it means is that imagine we have a map that depends a lot on output, on the perturbations of the out or of the input, sorry. So imagine we have an input and uh, a map, a function that maps this input to some output. And imagine we perturb this input by a very perturb it very have a very small perturbation, and suddenly the output changes completely. And these mappings are called chaotic maps. And this is how the turbulence in fluids is described. So imagine we have very small changes in the input, and there are very large changes in the output. And this is shown here. This is a 3D shear layer experiment. And these two inputs are close to each other, while the outputs are wildly different. So how do we mathematically describe this phenomenon? So in fact, for chaotic maps, for turbulence, instantaneous solutions lose their meanings. So we really need to resolve all the possible scales of the input and the output in order to get very precise mathematical descriptions of those mappings. Since we cannot usually do that, we cannot measure all the possible scales in the input. We have to observe statistical quantities and statistical solutions of PDEs. So statistical solutions are time-dependent measures where you start with some distribution in the input, and then you see how this distribution is evolved in time, where the Navier-Stokes equations, this is a very difficult point to explain, but we see how the solutions are evolved with the Navier-Stokes equations, and then we get kind of time-dependent distributions that describe our fluid flows. And it appears that the neural operators or all the different baselines that we tested out cannot approximate these mappings. So what happens, we described that in our paper, which is called Giant CFD, I'll speak about it very soon, is what happens is that the neural operators collapse to the mean of the distribution. So they approximate very well the mean of this time-dependent distribution or statistical solution of the PDE, but they cannot approximate the details of the solution. So here is one of the experiments we have. It's a 3D experiment. It's fluid-like data, and we see that neural operator is not even close to the ground truth. So how to approach these problems? We believe a very good approach is to use diffusion models or conditional diffusion models. So what those models do, they take a sample from a distribution, and there is a forward process of the diffusion that adds noise to the sample, and it's a time-dependent noise. So, and in the end of this process of adding the noise, we get something close to a Gaussian noise. And then to sample from this distribution, we go backward. It's called backward diffusion. And so we sample from a Gaussian-like distribution, and then we learn how to denoise this noisy sample in order to get the real sample. This can be done with UVIT, which is UNet with vision transformers added in between the encoder and the decoder. So what this UVIT does, so you have an input, a condition, and you have a noisy output. What this model should do is just denoise the output. And this paradigm is called conditional diffusion model. So you condition on the input. And it appears that once you have this denoiser, you can sample from the distribution. For instance, this is a Taylor Green, very famous 3D turbulent flow. So you see that, one second, just to move. So you see that in the first row, you have the ground truth samples, and then we sample from our diffusion model, and we get the samples in the middle. We call this paradigm GenCFD, by the way, if you're interested in reading about it later. And we get very, at least visually accurate samples, while the neural operator again samples only those, the mean of the distribution, as I mentioned earlier. So now we observe how the distribution itself looks like. It seems that for any random point in the flow, so imagine you pick some random point in the flow and see how the Gen CFD distribution is compared to the true distribution, and it seems that, for instance, for this Taylor green flow, they match closely, while the green line on each plot here, it's a one of the baselines, one of the neural operators we tested out. You see, it's not peak. It's really like a delta Dirac delta distribution. So there is a collapse to one value, and the neural operator cannot really escape from this single approximation. And why these diffusion models matter? It's because they really decrease the amount of really decrease the computational time needed to obtain samples from these turbulent mod from these difficult distributions. For instance, here we have a nozzle experiment, and with the Lattice-Boltzmann numerical method, 3 hours and a half are needed to get one sample from a distribution, while with GenCFD we can get one sample in 1.5 seconds, which is orders of magnitude lower. And again, I showed here ground truth, GenCFD, and the neural operator in this case as well. You see that the neural operator collapses to the mean, while the generative model, the generative diffusion model here, gets very accurate, visually accurate samples. And also we saw that it gets also the accurate distributions. I also have the spectra. So you see this is a spectrum, the true spectrum of the Taylor green distribution. The orange line shows the approximated distribution using the diffusion model, while the two neural operators that we tested, or the regression model that we tested, collapse really. They don't approximate the spectrum very well. We also tested out the Wasserstein distances between the distributions. They're also very low when ground truth is compared to GenCFD, while they're very high when you compare them to the tested neural operators. And this shows that these diffusion models can't really approximate well the chaotic maps, while the neural operators cannot. So regarding the foundation models, at least today, they cannot approximate all the mappings that we can imagine, but in the future, we believe that they would be able to approximate a lot of different difficult problems. So thank you for your attention, and please let me know if you have any question.
Great, thank you, Bogdan. That was really nice. So, do you have any questions from the audience?
Yeah. Hi.
Yes,
my name is Divik.
Oh, sorry. Yeah, I
Yeah.
hear you now.
Yeah.
Hi.
My name is Divik. I'm a PhD student working with Professor Kaniadakis. Thank you for
Nice
the
to meet
great.
you.
I have a couple of questions actually.
Sure.
So let's start with the Gen CFD part regarding how you formulate the problem. I understand. Okay, that slide was good. with the UVIT. Yeah, that's a good slide. So I
This one.
understand that, yes, the conditioning part of the diffusion model will be the initial condition, let us say, or the state at
Yes.
certain time step t.
Yeah.
And you're trying to conditionally generate the state of the system at certain time step t plus delta t.
Yes.
So
So we actually trained the model to approximate essentially many time steps in the future. So you fix the time t equals 1 unit time. You can jump there. You can also jump it 2 unit times, 3 unit times, etc.
right. So probably then you need to ensure a consistency in physical time, right? So do you use the same noise for the
So we
data?
use the noise that depends on, so we condition on time. Every layer in the UVIT is conditioned on the physical time as well as the diffusion time.
Right. All right. All right. I understand. So now it makes sense. I agree. Yep. Thank you. Then what about the number of training samples you required for each
So
of
it
these?
really depends on the distribution. If the
Right. For example,
distribution
I had
is
something
very,
like that, right?
so for instance, for Taylor Green, we went to 2 unit times, which is a fully developed turbulence. We could train the model with 1,000 samples, or we haven't tested. We have it somewhere in the paper, but also you have
Right.
the scaling as well in the
Right.
diffusion. So
So
it really depends on the error you want to
right. When
get.
you say
But
samples, do you mean 1,000 different trajectories or a
yes,
single
yes,
trajectory
1,000
with
different simulations.
right. So what is the least number of
So you
s-
can train it with 128, for instance. We
for
tried
instance?
that.
All right.
So Taylor Green example is very easy in a
Yes.
sense. But for
Uh-huh.
instance, for this lattice Boltzmann, it was very, very difficult to train
Okay.
it. So we had problems. Our models could not converge, for instance, and you
Uh-huh.
need a few thousand samples,
Right.
which is a lot.
Yeah. Okay.
You can, of course, to get slightly worse approximations, you can go with 500.
Uh-huh.
But again,
Okay.
for UQ or design, you need sometimes millions of
Samples. Yeah.
simulations, and then
Right.
you would be able to get those
I
million
understand that.
samples much faster.
Yes, I agree. So another question is about the error metric. You said you use the Wasserstein distance between the distributions of the fields.
Yeah.
Uh, did you consider using like the structural similarity index, the SSIM, or the typical computer vision metrics?
We had typical computer vision metrics, but we believe they were not. We had in the first version of the paper we have this. I forgot the name of the metric.
SSIM.
No, we had a different metric.
And, okay.
We had a few computer vision
Okay. All
metrics
right.
you can check up in the first version,
Understood.
but
Yeah, sure.
they didn't really show. Uh,
What you
in
observe in
this,
the result.
you see
Yeah.
visually here the neural operator
Right.
is very bad, but in some of those metrics you don't see that it's very bad because
Right.
they're
Right.
they're dependent a lot on the mean of the distribution that you approximate, and then if
I
you don't
understand.
have these tails for some of the computer vision metrics, that's completely fine. You still get a low
Yeah.
metric. So we just decided to discard
Yeah.
them,
I
but we tested
experienced
them.
something very similar. That's why I asked the
Yeah.
question. Yeah. So you think the Wasserstein distance is a good metric of the field?
Also, we had this mean error, variance error. So you compute the variance,
Right.
approximate the variance, then compare it to the ground truth variance.
Uh-huh. Okay.
And then this is also very, very important metric for us. Because for instance, in
Okay.
this experiment, the variance is huge. And then
Uh-huh.
with neural operator, you have zero variance, almost zero
Uh-huh.
variance. And then with
Okay.
GenCFD, you have really huge variance.
Okay.
And it's like 20% in the variance error, 20% relative error in variance, which was
Okay.
amazing for us, at least in the nozzle experiment. But you can read the
Understood.
paper. We
Sure.
explained
Yeah.
why we use some
Metrics.
metrics
All
and
right.
why we use
All
some
right.
why we don't use some other metrics.
I'll refer that. Thank you. Okay, next I want to ask you about the convolutional neural operators, if that's all right. I have a couple
Sure.
of questions there as well. So my main question is about your upsampling and the downsampling operation. Like I think
Yeah.
it's on next slides. Uh,
Let's say here.
oh, I think the next slide. Yeah, that one.
Okay.
So, so I see here by upsampling, I think you are representing the same signal on a much more
we
dense grid.
represent the same continuous signal with the upsampling if your upsampling is smart upsampling with quotation marks. So how we use this upsample? It's we use these windowed sync filters. In this case, it's Kaiser window sync filter, and this is a discrete filter, and it has finite impulse response, and it's approximation of the sync interpolation filter that you could use for up and down sampling. And in our case, since you are on a computer, you have to approximate this sync interpolation filter. You use these window sync filters, and basically it's a convolution. You apply the convolution of the signal and this sync filter with an additional step. You can up or down sample. This additional step is adding zeros random in between the samples. If you want to upsample, for instance, by a factor of 2, you add zeros, and then you filter out the high frequencies. And then you get the same signal, but only upsampled. Essentially the same. So again, it's not perfect by any mean, but it's a good approximation.
Yep. Why is it better than, let's say, linear interpolation? Or I think
So linear
essentially
interpolation introduces a lot of this aliasing. So you lose this
right.
equivalence.
Right.
This
Okay.
slide.
Okay. I understood. So that's where the research went. I understand. Yeah. All right.
Yeah.
And did you by any chance study? So I understood, like, for a given Nyquist sampling frequency of the grid and the given characteristic signal, characteristic frequency of the given signal and the actuation you're using, you experience this aliasing. Did you by any chance see what is the relationship between this Nyquist frequency and the characteristic frequency of the signal? Like I assume, like if you have a sufficiently dense grid, which is close to the uh, upsampled frequency of your upsampled grid, in the first place, you probably will not have the aliasing, right?
But
Yeah.
most of the aliasing, I believe, happens in these layers in the UNet. Because you have a very low
Very
sampling
coarse
rate.
grid. Yes, we have very low. Yes, that's true.
Let's say 4 times 4, 8 times 8. And then there, all the frequencies are important in the signal.
Right.
So there are no low frequencies essentially. And once you apply the activation function, a lot of new frequencies get introduced on top of these low frequencies.
Okay. Okay. So that upsampling and downsampling part that you introduce is most critical in the lower levels of the unit, you're saying.
Yeah, sometimes, for instance, the FNO could use the aliasing to get better. So the aliasing is not per se the very bad thing. It could be used also to enhance the performance, but in a purely mathematical way, we believe that if you enforce this CDE, continuous discrete equivalence, you get at least better mathematical description of your model and also better performance by lowering the aliasing error.
All right. Thank you. I just have one last question,
Sure.
which is about in the Poseidon part in the one of the earlier slides where you're showing the scaling. Yep. So I understand you use a transformer-based foundation model that was pre-trained on a bunch of different data sets.
Yes.
After which it exhibits very nice scaling behavior. But my
Yes.
question is, suppose you have like a transformer, same architecture, whatever you're using, but let us say 0.82 million for a fair comparison with the CNO here.
Yeah.
Same parameter, but you don't do any pre-training.
So that's what we have done. So here I just showed that the CNO scales well with the low amount.
Yeah.
So the small CNO models can scale very well as well as the
Large.
large or
I was wondering how well the transformer-based model will fit in that same curve.
So
Without,
we have it in the Poseidon paper. We also
all right,
trained from scratch the transformer models.
with
and
same number of parameters like the CNO.
So when you increase the number of parameters the model itself is not a CNO, it's a transformer
Right.
here in the Poseidon. And we
Uh-huh.
compare, so if you increase the number of parameters to the number of parameters that the foundation model has, then you get worse performance than comparing to the model that has a slightly lower number of parameters. So imagine you have a 150 million parameter model and 30 million parameter model. 150 parameter model it's very data hungry. It needs a lot of data to get some reasonable performance. So
Right.
since we are in low data regime, it's much more fair to compare the performance to the model that has a lower number of parameters, so like 20
Right.
million, because we are in this low data regime. But foundation models are not in
Right.
this
Right.
regime because you already
Right.
pre-train, you precondition
Right.
them
Right. Right.
essentially,
Yeah.
and yeah.
Yeah, I just want to know because I am personally working with problems where the samples are very, very less. And I had I felt like unit-based architectures were working better when the
Yes,
samples were very
because
less. By very
they
less, I mean I have like one trajectory with like 150 snapshots.
So the issue with the transformers is that they are very, very data hungry. So you need a
Right,
lot of samples to push them to this scaling plot. So you see
right.
here for Poisson equation, there is some
Uh,
scaling in the beginning with the
uh-huh,
low alpha, and then
uh-huh.
suddenly there is a higher scaling.
Right. But this is the pre-trained one, right?
There is a similar performance with the one trained from
Scratch
scratch.
model.
It's
Okay.
just above, like
The FNO part.
yeah.
Yeah. Okay. Yeah, sure. Right.
So
Yeah,
it's
I
like here, but
uh-huh.
it has similar this I don't know kink here
Yep. But you're saying it will be worse than the CNO or the unit.
in the low data regime. In the high
Low
data
data.
regime, so
Yes.
it really depends on the problem. I
Yes.
cannot tell
Yes.
for
I was
your
speaking
problem.
about the low data regime only.
But
Yes.
in the
Thank
low
you.
data regime, it's probably better to use some
Attention based.
non-transformer architectures, but
Yeah.
some
I understand.
FNO, CNO, or I don't know, UNet.
Right. Yeah, I just want to verify with someone else who is doing something similar because I experienced something very similar. So
Yeah,
I just want to validate with you.
that's
But
what
thank
we
you right
observe,
now.
and not just me, but many people in my
Many
group.
people. Yeah, perfect. Yeah. Thank you. Thanks for the
You're
great talk.
welcome.
Nice. Do you have any other questions? I think that Ahmed had another question. Here.
Oh yeah, I have a short question about the
Hello.
GNCF. Hi.
Yes,
Thanks for the presentation. It was really, really nice.
you're welcome.
So about the Telogene vortex flow.
Yes.
So my question is that, so with this GenCFD, can you like predict, in TGV, we are interested in the time evolution of energy dissipation, for example, right?
Yeah.
So would you be able to predict that? Like, let's say you input the Reynolds number and then
So,
using,
oh, sorry. So what we are able to predict in TGV, just a sec, is basically distributions around the training times. So we cannot predict too much into the future or extrapolate in time. And so let's say interpolation times, we can predict the energy as well very accurately. So the spectra, yeah. And we can predict essentially all the statistical properties needed because we are even point-wise accurate.
but
So
the point-wise is not accurate, right? Like if you look at the TGV, the
yes,
point-wise is not accurate, right? So depending at what, so TGV is about mimicking the laminar to turbulence transition.
yes,
And as you go through time, you may get more smaller scales, And then
yeah.
so
So sorry. Yeah, I forgot. We had this experiment in TGV. Again, the turbulence pops up, let's say after some time t.
yeah,
So the diffusion models are able to predict predict the laminar flow from
Mhm.
0 to turbulent beginning of turbulence, and also they're able with the same model to predict the turbulence as well accurately.
So then the time evolution would be accurate if you train it on enough
Yes, it would be
samples and
accurate.
enough. So have you tried that? Because
So we tried
if
this laminar to turbulent switch, and it worked. We also provided the details in the paper, but I mean, we didn't really go into details. We just observed all the problems in the same way. So can we predict the spectra? Can we predict is the Wasserstein distance large? Can we predict the variance, the mean, or statistical quantities that are related to any distribution, not just the TGV?
Mhm.
But I'm pretty
Okay.
sure that all the statistical quantities are well approximated, at least in this training window.
But I'm not sure because I'm not sure. So you have to try it. We have like average statistics, first order, second order,
We also tried
and
second order statistics, third
uh,
order. Second order
mhm,
is variance, but third order, fourth order statistics, it's very
is
accurate.
one. Okay.
So we actually had, someone asked us to do that, and we tested it out. It works very well.
Okay. Okay. Perfect. Thank you.
Thank you.
Great. Do you have any other questions?
Just one last question for the Gen CFD.
Sure.
How many iterative denoising steps did you require?
We also tested out the model with the varying number of diffusion steps. You can go from 16 to 128.
Yeah,
And with 16 already, it's quite accurate.
pretty good. All right. And I assume you will be using like a deterministic sampler, right?
No, we use the stochastic sampler.
So my question, so if you're using a stochastic sampler, doesn't the generated trajectory have temporal discontinuity across time steps?
So there are two times, right? There is the diffusion time and there is
Right.
the physical time. The
So
physical
when you
time
do
is,
the actual physical time, I understand. My question is, if you use a stochastic sampler in the diffusion time,
of course,
the
you use so it's discretized sampler,
right,
stochastic sampler. So you use
yes,
just let's say, Euler Maruyama sampler
yeah.
to get the sample. I'm not sure I got your question.
So my question is like during each iteration of denoising used in the sampler, do you inject further noise? So there's a
No, I
that's
mean,
what
you go backwards. You sample
yes,
from a
in the
Gaussian and then you remove
process
noise.
remove noise, but
Yes.
there are some stochastic samplers that even during the sampling to enhance the variability, they
No. We don't inject the noise.
noise during sampling. All right, yeah,
Yeah,
all right,
so
yeah.
the noise could be injected in the inputs actually to
Only
get
at
the
the time step
variability.
zero, like the first at the
Exactly,
goal.
yeah. So in
Perfect.
the condition, not in the sampler itself.
Right. Yeah, that clears it. Yeah, thank you.
Welcome.
Great. Thank you so much. Do you have any other questions? It looks like we do not, so maybe it's time to call this seminar. Thank you so much, Bogdan, for this nice
Thank you very
presentation.
much.
Thank you for your time, and thank you everyone for joining us today. Until next week.
Bye. See you.
Bye.